welcome to Calico Con Cloud Native Security Summit 2022. I am Parth Goswami, Customer Enablement Engineer working at Cloudera and a Calico Big Cat, that is a community ambassador for Project Calico. I am a free and open source software enthusiast and mostly work with containers and networking. In my free time, I also regularly host meetups and interact with the community while contributing to open source in any possible way. Today, we'll be talking about managing IP addresses in Kubernetes. Let's dive into the agenda. In this agenda, we will start with the Kubernetes networking model. We will try to understand what CNI is and how pods get IP address. And then we'll move on to the introduction to what Calico IP address, basically how Calico approaches IP address management and what Calico IPAM is. We'll discuss what causes IP exhaustion and what are the consequences of IP exhaustion. And we'll see a use case where how Calico CNI solves IP address exhaustion on Microsoft AKS. Before we start with today's topic, let us briefly try to go through the basics of container networking, that is, what is Kubernetes networking model and how it works. Now, the Kubernetes networking model in itself demands its own session, so we will try to stick to the crux of it and do a quick walkthrough. We know that Kubernetes was built to run distributed systems over a cluster of machines. The very nature of distributed systems makes networking a central and necessary component of Kubernetes deployment. Understanding this Kubernetes networking model will allow us to correctly run, monitor, troubleshoot our applications running on top of Kubernetes. Networking is a vast space with a lot of mature technologies. For people unfamiliar with this landscape, this can be a bit uncomfortable because most people have existing preconceived notions about networking. There are a lot of both new and old concepts to understand. Maybe a non-exhaustive list might include technologies like network namespace, virtual interfaces, IP forwarding, network address translation. Having said that, networking is central part of Kubernetes, but it can be a bit challenging to understand exactly how it is expected to work. There are 5 distinct networking problems to address. First is highly coupled container to container communication. This is solved by pods and coalesced communication. Typically, we view network communications in a virtual machine as interacting directly with an Ethernet device. In reality, the situation is more subtle than that. In Linux, each running process communicates within a network namespace that provides a logical networking stack with its own routes, firewall rules, and network devices. In essence, a network namespace provides a brand new network stack for all the processes within the namespace. In terms of containers, a pod is a group of containers, we can say that, and that share a network namespace. Containers within a pod all have the same IP address and port space assigned through the network namespace assigned to the pod. And we can find each other via localhost since they reside in the same namespace. Pod-to-pod communications using IP within the same cluster. In Kubernetes, every pod has a real IP address. Each pod communicates with other pods using that IP address. If 2 different pods within the cluster or within the node or maybe within different nodes want to communicate, it should communicate using an IP address. Pods to service communication within the cluster. Kubernetes service manages the state of a set of pods, allowing you to track a set of pod IP addresses that are dynamically changing over time. Services act as an abstraction over pods and assign a single virtual IP address to a group of pod IP addresses. Any traffic addressed to this virtual IP will be routed to the set of pods that are associated with the virtual IP. This allows the set of pods associated with the service to change at any time. Clients only need to know the service's virtual IP, which does not change. Next, any external component also should be able to talk to the Kubernetes service, which is ingress, etc. And also Kubernetes networking model is saying that there is a shared namespace since these containers are Linux based. So this container should share network namespace. This is about the Kubernetes networking model in brief. In order to implement a Kubernetes networking model, Kubernetes introduced a CNI, container networking interface, rather a container network interface, which is nothing but a common set of standards, specifications, libraries, etc., which is managed by CNCF. CNI basically is a common specs for writing CNI plugins. Now, why do we need CNI plugins? It is basically needed to configure network interface. Since the containers are Linux based, we need network interface in Linux containers. That's what the CNI will basically try to solve. So the plugin specification defines an interface for configuring the network, provisioning the IP addresses, and maintaining connectivity with multiple hosts. Now, if you ask by whom CNI is used, it is mostly used by container runtimes such as Kubernetes, Podman, or Cryo. There are many more CNI supported runtimes, and if it is not supported, yes, there are some plugins that are available, like Calico, for example. Kubernetes CNI is required. So as we know that both Linux container and container networking technology are continuing to evolve to meet the needs of applications running in various environments and clusters. So the CNI is an initiative of the Cloud Native Computing Foundation, which specifies the configuration of Linux container network interfaces. CNI was actually created to make networking solutions integratable with a range of container orchestration systems and runtimes. Instead of making the networking solutions pluggable, it defines a common interface standard for both the networking and container execution layers. CNI also focuses on the connectivity of container networks and the removal of allocated resources upon the termination of containers. This focus makes CNI specifications simple and allows them to be widely adopted. So how does a CNI work? It's a bit simple, not that much difficult to understand. So let's say that a Kube API server is looking to talk to a particular node. Take any node. Basically, a node will have host network namespace. Kube API server will talk to kubelet. That's because the Kube API server's first point of contact is this kubelet. Kubelet will talk to the CRI plugin. Containerd is one of the CRI plugin. This containerd will go and create a pod network namespace. CRI will also trigger the CNI. This CNI will take care of networking solution such as linking the pod network namespace and host network namespace, adding routes, etc. So this CNI's job is to take care of the networking solutions, while CRI's job is to take care of the container specific solutions. This is basically how a CNI works. In the previous slide, we saw what a CNI is, why it is used, and how does it work. In this slide, let's try to understand that what exactly a CNI do. Basically, CNI takes care of connecting the pod into the network, meaning in the pod network, once a pod is created, how the pod will communicate to a network and API server, how the pod will communicate with other pods, service, etc., is something taken care of by CNI. How will it take care of it? By IP address management, which is also the topic of this session, managing IP addresses in Kubernetes. So assigning IP address is a part of CNI's job. CNI will insert network interface between the container and as well as the network namespace. CNI will make sure every pod will get one IP address. CNI will help create isolation. Pods are like a small replica of virtual machines where they run in their own namespace. CNI will isolate the pod using the network policies. Pods are a very lightweight virtual machine which runs Linux namespace. When used with Kubernetes, CNI can integrate smoothly with the kubelet to enable the use of overlay or underlay network to automatically configure the network between pods. Overlay network encapsulate network traffic using a virtual interface such as virtual extensible LAN or VXLAN. Underlay network work at the physical level and comprises of switches and routers. So once you have specified the type of network configuration type, the container runtime defines the network that containers join. The runtime adds the interface to the container namespace via a call to the CNI plugin and allocates the connected subnetwork routes via calls to the IP address management, that is IPAM plugin. Container networking on a single node or a one node cluster. So given the network namespaces that isolate each pod to their own networking stack, virtual Ethernet devices that connect each namespace to the root namespace, and a bridge that connects namespaces together, we are finally ready to send traffic between pods, but on the same node. So this is a worker node where the bottom portion is the host network namespace, whereas the first half portion is the pod network namespace. Every node will have a certain CIDR range assigned to it. Host network will have a ETH0 interface. There are two different containers in the same single node. This container will have individual IP addresses, and every container will have interface ETH0. The VETH pair, Ethernet pair, will be connected to the CNI bridge, CNI 0 bridge. This bridge will also have one IP address. By using this bridge, it will connect to these three dots. These three dots can be a kube proxy, kube DNS, etc. There can be many more interfaces in between. The communication then will take place internally within the node itself. Now, Kubernetes networking model dictates that pods must be reachable by their IP address across the nodes. That is, the IP address of a pod is always visible to other pods in the network, and each pod views its own IP address as the same as how other pods see it. We now turn to the problem of routing traffic between pods on different nodes in the next slide. Having worked out how to route packets between pods in the same node, we move on to routing traffic between pods on different nodes. In case of two different nodes, node 1 and node 2, whenever you install any one of the CNI, that CNI comes up with a VXLAN. VXLAN is an IP in IP where one IP packet is encapsulated in another IP packet. If container 1 wants to talk to container 2, then the traffic will traverse from a VX pair CNI bridge. This will have an IP through the VXLAN, and through this ETH0, the communication will take place. There will be an overlay network also, which will be used by the Calico. That's basically how the multi-container communication will happen. And this is an explanation brief. How do pods get assigned with an IP address? Say this is a master node and this is a worker node. Master node will have a Kube API server and a CNI plugin is installed. On the worker node, there will be a host network namespace by default. Now, let's say we execute a command to create a pod, something like kubectl run nginx pod hyphen image is equal to nginx. The command then calls the kubelet. Kubelet will call a CRI plugin, container runtime interface. This plugin is the container D as we discussed in one of the previous slides. Now, this CRI plugin will use the container D and will create a pod network. By pod network, I mean only the network namespace and C groups. Next, CRI plugin will trigger CNI to establish a network between the pod network and the host network. It will create a VETH pair, virtual Ethernet pair, attaching one end to the pod network namespace and other end to the host network namespace. Along with that, it will add a route to the host network namespace. This route is added so that the host knows there is a route established. The reason being, creating one pod in this case, and what if I create 100 pods, then 100 respective namespaces will be created. Even then, in case of that many pods, the host will be aware of that, and that's how it works. Moving on ahead, the CNI plugin will have a CRDS, like a bridge, IPAM, etc., which are installed by default. So the plugin, by using CRDS from its pool, will pick up one IP address and returns it to the CRI plugin. By the way, before returning the IPs to CRI plugin, index IDs will be created in the pod. Once the IP address is written and CRI creates index, a pod specific namespace will be shared and the sandbox container will be created for the first time. After that, the kubelet will instruct the CRI to pull the actual image of Nginx. If the image is not present locally, it will be pulled from registry. If it is present locally, container is created and it will be attached to its particular namespace. Namespace in the sense, the pod specific namespace, the IP address is assigned to the sandbox container, which is created by the CRI. CNI's job in this case is to take care of the network routes. IP address management, IPAM, is an integrated suite of tools to enable end-to-end planning. It also helps in deploying and managing and monitoring of your IP addresses or IP address infrastructure. IPAM automatically discovers IP address infrastructure servers and domain name system DNS servers on your network and enables you to manage them from a central interface. Kubernetes uses IPAM plugins to allocate and manage IP addresses assigned to pods. Different IPAM plugins provide different feature sets. Calico provides its own IPAM plugin called Calico IPAM or Calico-IPAM, which is designed to work well with Calico and includes a number of features. Different IPAM techniques provide different feature sets. Calico's IPAM provide additional IP allocation, efficiency, and flexibility compared to other or IP address management approaches. The Calico IPAM plugin uses Calico's IP pool resource to control how IP addresses are allocated to pods within the cluster. This is the default plugin used by most Calico installations. By default, Calico uses a single IP pool for the entire Kubernetes pod CIDR, but you can divide the pod CIDR into several pools. You can assign separate IP pools to particular selections of nodes or to teams, users, or applications within a cluster using namespaces. You can control which pools Calico uses for each pod using node selectors and annotation on the pod's namespace or an annotation on the pod. Calico also supports the host local IPAM plugin. We will see that in the next slide. Let's quickly go over as to how Calico's IPAM works at a high level. Its primary goal is to provide efficient usage of the cluster's IP address space in a way that's flexible enough to meet a variety of deployment architectures. At a high level, Calico uses IP pools to define what IP ranges are valid to use for allocating pod IP addresses. IP pools are configured by cluster administrators applied using Calico CTL. If using Calico's overlay mode, they can be any private network IP range, but many users don't use an overlay, however, and in that case, the IP pools must use addresses that are available on the underlying network environment. Within Calico's IPAM engine, this IP pools are subdivided into smaller chunks called blocks, which are then assigned to a particular node in the cluster. Blocks are allocated dynamically to nodes as the number of running pods grows or shrinks. In particular, this means that Calico is much more efficient in its use of IP addresses when only a few pods are running on a node, and at the same time doesn't impose any upper limit on the number of pods per node. The host local plugin, which we gave a quick introduction in the last slide. It is a simple IP address management plugin. Uses predetermined CIDRs statistically allocated to each node in order to choose addresses from pods. Once set, CIDR for a node cannot be modified. Pods can be assigned addresses only from within the CIDR allocated to the node. Calico can use the host local IPAM plugin using the node.spec.pod CIDR field in the Kubernetes API to determine the CIDR to use for each node. The host local IPAM plugin is primarily used by other methods of routing pod traffic from one host to another. For example, it is used when installing Calico for policy enforcement, flannel networking, as well as when using Calico in AKS, Azure Kubernetes Service, or Google Kubernetes Engine, that is GKE. IP exhaustion, IPv4 in particular, is a problem resulting from the unanticipated popularity of the internet at the time of its creation. It is a depletion of IP exhaustion is basically the depletion of available IPv4 addresses for connected device. Now, beginning in the early 1980s, each computer was assigned a unique public IP address consisting of four groups of 8 bits or 32 bits in total. The standard called IPv4 resulted in 4 billion different values. At that time, this supply obviously seemed inexhaustible, but by the late 1980s, it was already clear that even a pool this large would eventually run out. With the rapid expansion of internet users, always on devices like mobile device and IoT, the time is now upon us. IPv4 exhaustion poses critical problems for internet users and service providers that depend on IPv4. Any shortage or delay in IP address assignment to a device from a network can result in the degradation of even outright denial of service to the subscribed device. Managing IP addresses is an essential part of container networking. It is very often that users overlook this aspect when planning their application's networking requirement, especially for those small clusters with a limited number of workloads. Having said that, businesses are bound to grow, and this growth leads to bigger clusters and more workloads, which causes IPs to become a scarce commodity. For example, when the user uses pod IP addresses that can be routed outside the cluster, the IP address must be unique across the network at large. Different IP address ranges, also known as CIDR, classless interdomain routing, are needed for pods in each clusters when running multiple clusters. If the quantity of IP addresses is limited, the user has to allocate and budget this IP addresses regularly. When users exhaust the available IPs, it limits the application scale and creates management overhead. Further, unexpected and non-budgeted demand for IPs to address a surge in application usage may also cause the sudden unavailability of the application. In the last few slides, we saw what IPAM is, we understood what Calico IPAM is, tried to discuss the causes for IP exhaustion and what are its consequences. In this last slide of the session, we will see a use case how Calico CNI tries to solve IP address exhaustion on Microsoft AKS. Now, cloud native applications running on Kubernetes rely on container network plugins to establish workload communications. While Azure Kubernetes Service, AKS, provides several supported network options, KubeNet and Azure CNI, that addresses the needs of most deployments. Microsoft recently introduced the ability to bring your own networking solution called BYOCNI. It helps users address more advanced networking requirements. This new features enables AKS customers to run Calico networking on AKS. With Calico's APAM capabilities, users can address their scale, availability, and management issues related to IP addresses. Calico's IPAM allows users to stretch IP resources as much as possible by providing private networks within their cluster. Calico uses IP pools to define which IP ranges are valid to use for allocating pod IP addresses. These pools are configured by the administrator. When using Calico's overlay mode, pools can be any private network IP range. IP pools are also divided into blocks, which are then assigned to particular nodes in the cluster. Blocks are allocated dynamically to nodes as the number of running pods grows or shrinks. This ensures efficient use of IP addresses when only a few pods are running on a node, and also eliminates any upper limit on the number of pods per node. due to a constrained number of available IPs. To top it off, Calico's does IP allocation automatically, thus eliminating the scale and manageability issues related to IP exhaustion. Well, we have reached the end of the session where we started off by understanding the basics of container networking model, rather Kubernetes networking model. Then we tried to understand what CNI is and how exactly pods get assigned with IP addresses. Then we got introduced to Calico IPAM and the challenge of IP exhaustion, followed by what are the consequences of IP exhaustion. And at the last, try to understand a use case where how Calico CNI solves IP address exhaustion on Microsoft AKS. Thank you for attending this session, and I hope you are enjoying the rest of the summit.
Cloud-native applications can't be secured with the traditional security tools. You need a more active and granular level of security. Calico Cloud is an active cloud-native application protection platform that detects, prevents, and mitigates breaches in cloud-native applications. Let's look at how to secure your cloud-native environment at build time with Calico's container security. At build time, we want to make sure that images that the development team provides are clean and without major vulnerabilities or misconfigurations. All image registries are auto-populated and continuously scanned by Calico's scanning engine. I can also manually add new registries. It's very easy for me to see the results of the last scan from the scan results page. Pass-fail is color-coded with specific scores. Details about each vulnerability that impacts each image are available on the right side. I can control which images can be displayed to my environment using admission control policies. I am only allowing images with pass or worn scan results. I've also enforced an upper limit for the age of a scan result. Now, if any application developer attempts to deploy an image that doesn't pass the security criteria, it will automatically be blocked. Once you have the admission policies in place, you may come across a situation where the application developer is telling you that a particular vulnerability does not impact their code and the way in which they are using the affected library. In this case, you need to create an exception. Calico Cloud offers a number of options to scope the exception to a specific image version, any version of this image, or any image. In addition to scanning and assessment of images, I must ensure the Kubernetes environment is also secure and does not have any misconfigurations. Calico helps you continuously assess your Kubernetes configuration using compliance reports that assess your configuration against CIS benchmarks. I scheduled my CIS benchmark report to run every 24 hours. The number of nodes passing or failing the CIS benchmark tests is color-coded. And here are the top failed tests. I can also download the full report to get more insight on each test and how to mitigate its risk. At this stage, I have scanned all my images, allowed the deployment of only those that pass the security requirements, and I have also assessed my deployment environment against